Okay, so now what I want to try to cover as quickly as I can is torque. Let's do it in this order. I'm kind of piecing together things I've used for different classes in the past, so I'm sorry if it seems a little disjointed. I need a thing. Ah, where are my things?
It's so funny though.
I found one. Okay, so I'm gonna have to do this extremely fast because y'all get out in about what, 20 minutes?
Yep.
Okay. So let's talk about how we communicate objects rotating. Okay. So let's see if let's not start there. Let's start here. Okay, this thing. Actually, let's use the stool instead. That's probably a better way to do it. Watch this. Stool. If I kick it near the bottom, it translates. If I kick it near the top, it rotates. Why did it have a different effect depending on where I applied the force, right? Like I tried to apply the same force. Did y'all see, like I didn't kick it harder. I just changed kicking it at the bottom versus kicking it at the top. Does that make sense? Same force applied differently yields a different rotational result. Are we cool with that? You should be familiar with this, right? Anybody ever try to like move something really heavy and accidentally tip it over? You probably push too high, right? If you push lower, it's less likely to do that. The reason for this is that forces can have a rotational effect, or they could not have a rotational effect. It depends on how they're applied. Figuring out what that rotational effect is torque. So torque is all about the rotational effect of a force. There are probably more formal ways to define it, but I find that gets to the point more effectively. So torque, we're not getting like this totally new thing. We're just saying like, hey, if I apply a force this way, or this way, it will cause an object to rotate differently, right? And so what I want to do is I want to talk about like what makes forces have a better or worse rotational effect. And this is something that you're probably already intuitively aware of, right? I just want to bring it to the forefront of your thought. So let's do that. So the first obvious thing is it depends on how the force is applied, right? A little bit of language here that you're going to need. First is the idea of a fulcrum, which is the point about which an object rotates, right? Any of you guys Star Wars fans?
Yeah.
Have y'all seen Andor and also Rebels?
I know.
Oh, okay. There's this fun little Easter egg in there where timer's going off. So Ahsoka Tano was called Fulcrum. That was like her code name early on in the rebellion. And then I'm watching Andor. You guys seen that show? No? Okay. I'm gonna tell you anyways. So I'm watching Andor, and there's like this guy who's organizing this like spy network for the rebels. And the Empire comes up with a code name for him, which is Axis, which I think is a fun kind of throwback because Axis and Fulcrum are essentially the same terms. So you've got these two people that are both fundamentally serving the same purpose and have slightly different names. I just thought it was cute. Anyways, moving on. The other thing is you need to get familiar with the term lever arm. So the lever arm is the distance from the fulcrum, or the point of rotation, to where you apply it, right? So you should be able to see that where I pushed this before, the point of rotation is going to be around that leg there. Actually, let me put it here. The point of rotation is going to be around these legs here, right? And so if I push it down low, my lever arm is shorter than if I push it up top. You see that? Okay. Be careful with your lever arm. You want to make sure you're always measuring exactly from the point of rotation to the fulcrum. Here's an example of when that gets tricky, and AP likes to trick you with this kind of stuff. Like if I try to rotate this thing, you're going to be really tempted to call the lever arm length the length of this white pillar here. But it's not, because this doesn't rotate about the center. It rotates about the edge. So the lever arm is actually the distance from this to the edge. So you'll see some questions here where we have to like build a right triangle and use some trig to find the actual lever arm, right? So be careful. Don't just assume the thing that looks like it's the lever arm is. Make sure you're measuring from the point of rotation to the point that you're applying the force. Does that make any sense? Okay. All right. So let's get into it. First, you should be familiar with this idea, but let's do it. Here's a door. If you're going to open a door, is it easier to open it by pushing away from the hinge? So the hinges are the pointy bits, the little cylinder bits over here that make it rotate. Is it easier to push it open over here or over here, like near the hinge?
Away.
It's easier to push it from far away, right? This is where normally I would have had you get up and do it to remind you of how doors work. There's a reason the handle is always way over on the other side. It's because that's the easiest place to open the door. Make sense? So the first thing we can learn from that is that the length of the lever arm is important. The longer the lever arm, the more rotational effect that force will have. Does that make sense? Lesson number 1. The next one, I actually don't have the right setup to show you. But the short answer here is the angle at which you apply a force also matters. If you push something square, right, like if I push on the door perpendicular to the door, it's going to rotate more easily than if I apply that same force at an angle. Okay? And that's something where, like, normally I take strings and I tie it onto these and have you guys try to pull them over, changing the angle. And then you can feel it's really easy when you're perpendicular to the lever arm. It's really hard when you're not. So the takeaway there is that the angle at which you pull the thing affects how hard it is to rotate it. Does that make sense? Okay. So what this tells us is, first, the further away you push, the easier it is to cause a rotation. Second, the more squarely you apply the force, the easier it is to cause a rotation. And third, the obvious one is the harder you push, the more rotation, which should be really obvious, right? What this brings us to is that I can take those ideas and I can combine them into mathematical statements so that I can describe the rotational force, the rotational effect of a force using math. And we call that rotational effect torque. So let's say this is like the door or something, right? So the orange thing represents whatever the thing is that we're rotating. The little like tannish brown circle, that is representing the fulcrum. And then the green arrow is the force that I'm applying. So if I think through what's happening here.
Lawson, I need attendance, please, for first period.
Okay.
Thank you, sir.
So the length of the lever arm there would be R, right? I'm going to label that R. And this force, you could say, has two components. One component that's perpendicular to that lever arm, which I've called F perpendicular there, and one that's parallel to that lever arm, right? Well, it turns out we only care about the force that's perpendicular, right? It's similar to when we talked about work, where I only cared about the force that was parallel. Similar idea here. When I look at torque, I only care about the component of the force that's perpendicular. So if I look at this, I could then say, well, if the angle's over here, between the lever arm and the force, F perpendicular would be F sine theta, right? Hopefully you're cool with that. And if that is F sine theta, and I apply all the principles I said before, then torque, which we label with a lowercase tau, it's over here, it's another Greek letter. We use all the Greek letters with rotation, by the way. Torque is equal to the lever arm length multiplied by the perpendicular component of the force, which we just said was F sine theta. Does that make any sense? Yes, no, maybe? I don't even know what I just said, Mamarachi. It's on video. Look. Go listen to future me. To try and repeat it, torque is going to be equal to the length of the lever arm, R, multiplied by the perpendicular component of the force, which is F sine theta, according to the algebra we did before. This is one of those times that I really want you to understand the important bit is actually R times F perpendicular, but you'll most often see it written as R F sine theta, and the reason for that is because they're finding the perpendicular component using the angle between the force and the lever arm. So you can use RF sine theta as long as theta is the angle between the force and the lever arm. If you don't have that angle, go look at how to find the perpendicular component of the force with whatever angle you're given. Does that make any sense? Okay. All right, that's it. That's all I have for that one. Now, quickly, I want to talk to you guys about equilibrium. And this will be a very quick talk. So equilibrium is this idea that something is not accelerating, right? We've seen that before. The first condition of equilibrium that we saw, hold on, is that you have to have a net force of 0, right? All the forces have to 0. We've seen that before. We talked about all that stuff with forces. Well, it turns out there's a second condition for equilibrium. So the first one is that force is 0. The second one is that the net torque is 0. So when we look at equilibrium, basically the idea is I can't have a linear acceleration, nor can I have an angular acceleration, which means that I can't have a net force, and I can't have a net torque. Does that make sense? So those are the two conditions for equilibrium. You will see lots of really difficult problems where you'll have to create a whole system of equations based on both of those ideas. The first one being the net force is 0, the other one being the net torque is 0. So when you get to these problems about something that might rotate, you've got to do Newton's second law statements because that's how we deal with translational equilibrium. But then there's also an analogous Newton's second law statement for rotation, which we will talk about tomorrow. Okay, so keep that in your mind for now, is that we've got the same idea. Very quickly, I don't have much time to do this, but we'll talk about center of gravity. It's actually one of the things I like talking about, but I don't have time to do it, because I think it's very applicable to like your life. Okay, so center of gravity is this hypothetical point where I can believe that gravity acts on an object, right? So you've probably heard this before. Like one of the places I hear this a lot is like when they talk about football players. Like Taj Brooks is a great running back, and one of the reasons they say that is because he's number one, a little short, but number two, he's good at getting low when he runs, which lowers his center of gravity, right? So like a normal human, their center of gravity is probably like here-ish. Actually, it's probably more like here-ish, but if I squat down, I'm lowering that closer to the ground, which is going to make me harder to tackle because it makes me harder to rotate. Whole lot of physics there I'd love to explain, but we don't have time for. Well, you need to know how to find that, right? So if an object is geometric, its center of gravity is at its center, right? It's geometric center. If it's not, you've got equations you can use to find it. And normally you have to find that by looking at where the center of gravity is lying along an x-axis, where it's lying along a y-axis, and you'll never do this, but if you have a three-dimensional object, you want to look at where it's lying along the z-axis. And here's how you do that. You do a little summation where for every mass, you say, hey, here's the mass, and here's its position, and you multiply them, and you add all those up, and you divide that by the total mass of the object. The only time you'll be asked to do this is if it's like, you have a discrete number of objects. Like I've seen fun little problems about like people dancing on a dance floor. And so it's like you have 3 different couples in different locations and you have to find the center of gravity of the dance floor. So the point being, there's just 3 objects that you have to consider. So you won't see like a whole bunch of craziness. If you apply calculus to this, you'll get some of the stuff that we'll talk about tomorrow. Which brings us to an interesting point about balancing things. So basically, things are balanced or can balance when their center of gravity remains within the support structure. Because what I need is that for my force of gravity, which has a torque, I need my force of gravity to have a counter torque. right? So like, look at this guy. When you look at this object, the force of gravity is kind of causing it to have a torque that direction to rotate it, but the ground is there to provide a counter torque the other direction. So it ends up not rotating, it stays at equilibrium. Does that make any sense? With this object though, because this torque is going to rotate it this way, there's nothing in the way. And so it won't have a counter torque to oppose that gravity. It'll just rotate about this point and fall over. And so it's just like a simple principle to understand why things balance. It's because they need a support structure under the center of gravity. This is like, if you want to know how to balance anything, so I think I ranted to you guys about that halftime show earlier this year, right? If you don't know how to balance anything, the first step is figuring out where its center of gravity is, right? So like, here's this thing. Its center of gravity is probably like here. And so if I want to balance it, I need my fingers to be under that point. And if I can keep my fingers under that point, then it'll balance. And this is actually a really easy object to balance, but whatever. If you want to balance something that's harder, like this, then you have to figure out where its center of gravity is and put it under it. So the center of gravity for this is probably like here. And so if I want to balance it, I need to keep the center of gravity under that.
Maybe don't try it.
No, I got it. We're good.
No, I don't think you got it at all.
I don't think you should talk.
Hey!
So you just have to put the center of gravity above the support structure, and then it'll balance. So, little side lesson there. So that's it. That's all there. Tomorrow we'll talk about moment of inertia. We'll talk about rotational energy, and we'll talk about angular momentum. So there's a few topics to cover tomorrow. It will be very fast and quick. But since I won't see you guys on Wednesday, I need to get it covered tomorrow. Or sorry, I won't see you guys on Thursday. Since I won't see you on Thursday, I need to get it covered tomorrow so that on Friday we can have your party and then just be done. Cool. Okay, that's it. Thank you for your attention if you listened, and thank you for being quiet if you didn't.